Let's now formalize the naive Bayes classifier. In classification, we have a document D and a class C. And our goal is to compute the probability for each class of its conditional probability given a document. And we're going to see that we're going to use this probability to pick the best class. Now, how do we compute the probability of a class given a document? By Bayes' rule, this is equal to the probability of the document given the class times the probability of the class over the probability of the document. So let's see how to use that in the classifier. The best class, the maximum a posteriori class, the class that we're looking for to assign this document to, is out of all classes, the one that maximizes the probability of that class given the document. So we're looking for the class whose probability given the document is greatest. By Bayes' rule, that's the same, whichever class maximizes probability of C given D also maximizes this equation, the probability of D given C, probability of the class over the probability of the document. And as is traditional in Bayesian classification, whichever class maximizes this equation also maximizes this equation. And what we've done here is we've dropped the denominator, crossed out the denominator. Why is it okay to cross out the denominator D? Probability of D is how likely the document is. Now, if I give you a document and I say, which of these 10 classes does this document belong to? And for each of these classes, I'm computing the probability of the document given the class, the probability of the class, and the probability of the document. The probability of the document is identical for all 10 classes. For each class, one more time, I have to compute the probability of the document. And that means that if I'm comparing 10 things, each of which is divided by probability of the document, the probability of the document is a constant. And I can eliminate that. So the most likely class, CMAP, is that class which maximizes the product of two probabilities. The probability of the document given the class, we'll call that the likelihood, and the probability of the class, we'll call that the prior probability of the class. So the most likely class is the one that maximizes the product of these two probabilities. The probability of the class will turn out to be relatively simple to compute. What do I mean by the probability of a document given the class? What do I mean to say this particular movie review was how likely is it given the class positive? It seems like a very complicated and confusing thing to compute. And one way to operationalize that is to say, let's represent the document by a whole set of features, x1 through xn. So when I say the probability of a document given a class, I'm going to say that all that means is the probability of a vector of features given the class. P of D given C, we're going to represent that probability by the joint probability of x1, x2, up through xn given the class. In other words, we're representing this document D as a set of features x1 through xn. That still doesn't tell me how to compute this probability, but it's a start. So let's talk about these two pieces now. How do I compute probability of a class? Well, really that's just asking, how often does this class occur? Are positive reviews much more common than negative reviews? Is Madison a much more frequent author? So to decide computing the probability of a class can be done just by counting relative frequencies in some corpus or data set. So the probability of a class is relatively easy to compute. What about the likelihood of the document, of these features in a document, given the class? Well, there's a lot of parameters for this probability. If there's n different features, and each of them has a certain length, that's a lot of parameters that have to be computed. and we have to compute them one for each class. So that's far too many parameters that we could possibly compute. We can only estimate this number if we had a huge number of training examples, and we usually don't have such an enormous amount of training examples. So we're going to make some simplifying assumptions in the naive Bayes classifier to make this computation more possible. The first simplifying assumption we're going to make is called the bag of words assumption. And we're going to assume that the position in the document doesn't matter. So this is what I gave you the intuition of a few slides ago. The position of the word in the document, whether it's the first word or the 7th word or the 150th word, isn't going to matter. All we care about is which word or which feature occurs. And the second assumption we're going to make is we're going to assume that the different features, x1, x2, x3, that their probabilities are independent given the class. So that whether one feature occurs given a class and whether another feature occurs given a class are independently going to be true. And of course, this is both of these assumptions are incorrect simplifying assumptions. They're absolutely wrong. They're terribly, completely not true. Nonetheless, by making these incorrect simplifying assumptions, we can make our problem so much simpler that in practice, we're able to solve the problem with a high degree of accuracy despite the simplifications. So the result of these two simplifying assumptions is we're going to represent the probability, the joint probability of a whole set of features, x1 through x1, conditioned on a class as the product of a whole bunch of independent probabilities. Probability of x1 given the class, probability of x2 given the class, probability of x3 given the class, and so on, up to probability of xn given the class. We're just going to multiply them all together. We're not going to care about x1, which position it occurred in. All we care about is that it was this particular word or feature, and we're not going to care about the dependencies between x1 and x2. In other words, in order to compute our simplifying naive Bayes assumption to compute the most likely class by multiplying a likelihood, the probability of a whole joint string of features, times a probability of a class, we're going to simplify that and say that the best class by the naive Bayes assumption is that class that maximizes these the prior probability of the class. So that's the same. But now, more simply, we're just going to multiply for every feature in the set of features the probability of that feature given the class. Much simpler equation. So now looking specifically at text, first we're going to assume we're going to look at all positions, all word positions in a text document. So we have a text document and it has 100 words in it. So for position of word number 1, position number 2, position number 3, we're going to take look at all the classes, and for each class we're going to say what's the probability of the class, and then for each class we're going to walk through every position in the text, and for each position we're going to look at the word in that position and ask what's its probability given the class I'm looking at. So we'll do this for class 1. We'll compute P of class 1 times the product over all the i's of P of word I given class 1. So we'll compute that, and then we'll do the same thing for class 2. For class 2, we'll compute P of class 2, and then the product over all positions I of the P of word I given class 2. And then we're going to pick whichever of these two is the highest. If this is higher, we're going to pick class 2 and assign it to the document. If this is higher, we'll assign class 1 to the document. And of course, I've shown you this with just 2 classes, but in general, this is true for any number of classes. So that's the formalization of the naive Bayes classifier.